Lecture number 5, the short history of the atom. So this time we're going to start with where we started at the beginning of the semester and looking at our scheme of different types of matter, which we then can break into substances versus mixture. Now we're going to spend some more time talking about this difference between elements and compounds. And we'll come back to mixtures at the end of the chapter, but right now we're going to start really delving into what makes elements and what makes compounds. And we're going to start on the element sides in this pure substances. We're going to talk about what are these elements made of. To do this, we have to sort of understand several underlying laws. These are things that have, if we remember back to the scientific method lecture, that have undergone a large amount of observation and seem to hold true all the time. So the first one of these is the law of conservation of mass, or mass conservation. It says the total mass of a substance cannot change during a chemical reaction. So we can think about this. Otherwise, that mass can't be created or destroyed. So if we look at a reaction where we take lead nitrate and sodium chromate, mix them together to form this new complex, we see that the mass we have at the beginning of that reaction, when they're two separate things, is going to be the same as the mass we have at the end when those are combined to form this new yellow precipitate. Right? So mass, regardless of what reaction we do, the mass at the beginning equals the mass at the end. The next is the law of definite proportions, that the different samples of the same compound always contain constituent elements in the same proportion by mass. So if we take mass, or atoms of mass, or element X, that have some mass, and atoms of element Y, combine those together to get this new compound, X and Y, that when they do that, they always form this same ratio by mass. So whenever we combine X and Y, we're going to get a mass ratio that's the same. The law of multiple proportions, if two elements combine to form more than one compound, so they can form two compounds, the ratios of those masses are small whole numbers. So for example, if we look at carbon monoxide versus carbon dioxide. Carbon monoxide, there's one oxygen for one carbon. And for carbon dioxide, there's two oxygens for every one carbon. So if we look at the ratio between those, the carbon dioxide to carbon monoxide, it's 2 to 1. So it's a small whole number. So whenever we combine two elements to form these compounds, if there's different ratios, the ratio between those by mass is going to be a small whole number. So factors of 2, 4, 3, 4, 5, so on. So that we're simply multiplying these factors by small numbers. So it may seem pretty straightforward to us now looking back, but when Dalton was looking at this data and looking at the information that he had available, he came up with a theory in 1808 to explain what he was seeing. Right? And to us right now, looking back on it, it seems fairly straightforward, but remember, this was in 1808. Not a lot of work is done. The instrumentation that they were using was fairly rudimentary, but he came up with this idea for an atom. He took all the information he had before, and he proposed this model. The elements, these things that aren't able to break apart anymore without changing, are composed of small particles which he called atoms. All of the atoms of this type of element are identical. So they have the same mass, the same size, they behave the same, they have the same chemical properties. And then if you take these atoms, combine them, you'll get these compounds. So compounds are atoms of more than one element. So you're taking two things, combine them together, you get the compounds. And the ratio of these atoms of each element present in the compound is either an integer or a small fraction. So it's the same sort of thing we've talked about before. So he took that idea of this law of definite proportions and was relating it then to his new theory of the atom. And then the chemical reactions involve only separation, combination, or rearrangement of these atoms. So they're not changing at all, they're just separating, combining, or rearranging the atoms. So we're looking here, he took the law of mass conservation. This now theory of these atoms, but again, we're not able to see atoms at this point, He just has this theory that this is what's going on based on the observations that he and others are making. And what we're talking about is what we call a cathode ray tube. We're going to use this to sort of look at some previous experiments that they did to help us understand this atom a little bit more. So a cathode ray is a charged tube filled with a gas, and we flow energy through that tube. All right, so you can see here that the tube, the gas is green, energy is flowing through it. We get this nice white light. If we then introduce a magnetic field to this flow of energy, we see that we can get it to bend. If we use one pole, we get it to bend one way. The other pole will cause it to bend in the other direction. So there's an interaction between this flowing energy and this magnetic field. So J.J. Thomson, who later won the Nobel Prize in 1906 in physics for his work using the cathode ray tube, was doing this. And based on the potential, the charge he was generating in this cathode ray, plus the magnetic field, he was able to calculate the mass to charge ratio of the particle that was flowing through this tube, which he called the electron. And he calculated the mass to charge ratio to be a negative 1.76 times 10 to the 8th coulombs per gram. So he proposed that within these, we have this particle called the electron. It's negatively charged, and it has a certain mass to charge ratio. It explains, while it's flowing through this tube, we get it to interact with this magnetic field. Later, R.A. Milken came back, which he won the Nobel Prize in 1923, was doing this. He was taking these fine drops of oil, introducing them to a can. It's called the oil can experiment. You interject this spray or atomize very small particles of oil into this container. They sort of settle through between these two charged plates, and by manipulating the charge of the plates, he could actually change the way those fine drops fell. In fact, he was able to get some of these oil drops to actually hover and stay stationary in the middle of these two charged plates and extract more information about this electron. So from this, he was able to calculate the charge of the electron being a negative 1.60 times 10 to the 19th coulombs. If you remember, we already have the mass to charge ratio. So then we divide those two. We get out now, from Milken's experiment, we can now get the charge of the electron, but also its mass, the 9.10 times 10 to the negative 23 grams. So now we're sort of nailing down these particles. They're back to Thomson's model. It says, okay, now we have this, we know an atom is neutral. And now from these previous two experiments, we know that there's some charged particle in there, this negatively charged particle. So how does that balance out? Right? So one of the theories was that the so-called plum pudding model, that we have these distinct locations of negatively charged particles sort of flowing in this positively charged goo. Let's say that. So sort of like he described it as plums within pudding. That's why we call it the plum pudding model. That was one sort of common hypothesis to explain while atoms themselves are neutrally charged, but we have this negatively charged electron. How we work that out. Well, Rutherford came back and started doing experiments where he said, okay, let's take some really thin element, in this case gold foil, and let's see if we can pass energy through it. Energy he chose to pass through was the alpha particle. So it's a positively charged particle, fairly large in mass. And since the electron is very small, if it's sort of suspended in this goo, positively shaped goo, by passing this through, there should be very little interference of those small particles. So he was predicting, his hypothesis was that these alpha particles were going to simply pass straight through the foil. Right? There could be no interaction between these large alpha particles and these very small electrons. Well, what he found was actually something very different. He found that while a large portion of those alpha particles passed straight through. A large, or some percentage, were actually deflected, either refracted straight back or bounced off at an angle. So they must have been hitting something else, something of significant mass. That as these large alpha particles came through, they must have contacted something in a fairly regular, repeating manner. So we did this several times and got this diffraction pattern that was very the same. So what he proposed, took his model, helped fit his observations. He said, no, there must be within this atom a tightly concentrated nucleus, something that has more mass. And that those masses must be concentrated in one place, which he called the nucleus. And furthermore, based on the angles that he was measuring, he could actually calculate what was in that nucleus, which he called the proton. It was a positively charged particle that had a mass of about 1.67 times 10 to the negative 24 grams. So he was able now to take his observations, readapt the model to fit these new observations. So now we have this new picture of the atom where we have in the nucleus, in the center, a tightly packed set of matter that has the proton. And then surrounding that mostly empty space, we have these very small electrons. So if we look at what Chadwick did in his experiments, he looked at that mass and said, okay, if we double the number of protons, so we go from hydrogen atom to the helium atom, where we go from 1 to 2 protons, then if this model is correct, we should get a mass then of 2. But what we see when we look at the mass of the helium versus the mass of the hydrogen isn't 2, it's 4. So there must be something else involved here in this nucleus. And what Chadwick said was that inside the nucleus there must be an additional particle, which we'll call the neutron. It's neutrally charged, no charge, and is about the same mass as that of the proton. Therefore, that accounts for this change in observation of mass of the helium to hydrogen. So now we have in this nucleus the proton and the neutron. Very far in the cloud we have this electrons. So in the current model, nucleus in the middle, protons and neutrons. Protons positively charged, neutrons negatively charged, and a distance of about 5 times 10 to the negative 15th meters. And within that larger atom, which has an approximate distance of 1 times 10 to the negative 10th meters, we have those electrons going out. The mass of the proton is about that of the neutron, which is both about 1,840 times that of the electron.
Dad, I didn't get it.